Well, good morning, students. Hey, it's Monday, 5/18/20. I hope you had a good weekend. Time for some earth science. So, last time we started looking at water. Water is such an amazing molecule. It just behaves unlike anything else out there. I mean, there's other things that have some of the properties, but water is just unique. And it's so important because without water being the way it is, we wouldn't be here. So today, in our effort to understand water better, we're going to, let's see, I can define what it means for a molecule to be polar. I can name and explain some polar properties of water, including ability to dissolve other substances, high surface tension, high boiling point, and high heat capacity. Those are all things that we're going for today. Water, we're going to see, is a very polar substance, and that leads to those properties. So, let's imagine this is a molecule. Now we've, I've used these models. So like this could be our water molecule, where this is an oxygen, and here's a hydrogen, and here's a hydrogen. And remember, on the other side, I showed you that there were pairs of electrons that weren't involved in a bond. And I said that oxygen attracts electrons more strongly than hydrogen. So these electrons that are being shared between the two, remember, both atoms are trying to grab hold of the same electrons. Well, those electrons are being pulled a little bit that way, towards the oxygen. And the same with this bond down here. Those electrons are being pulled towards the oxygen more than the hydrogen. And because electrons are negative, remember, they're the negative subatomic particles, that means that this oxygen over here gets to be a little bit negative, and this hydrogen over here gets to be a little bit positive. And so when I look at this molecule, there's a positive side and a negative side. That's a polar molecule. Polar simply means it has ends, in this case oppositely charged ends. A polar molecule has ends. Now, not all molecules are polar. If you look at this molecule, this could be a molecule of methane. Methane is the primary component of natural gas. When we use our burners in the lab, we're burning primarily methane. So methane has got 4 bonds. There's a carbon in the middle and 4 hydrogens around the outside. And while these bonds might even be slightly polar, there might be a slight imbalance. There probably is a little imbalance in which of these atoms attracts electrons more strongly. Do you notice how, there's a hydrogen sticking out here, and there's a hydrogen sticking out down here, and one over here, and one over here. And because the hydrogens are spread all around the middle, it balances things out. So that there's no, let's just imagine for right now that this hydrogen is slightly positive compared to that carbon right there. It's slightly positive. So if I had some sort of charge probe and I come over here, I'd be noticing positive. But if I come over here, I'd be noticing positive. And if I come over here, I'd be noticing positive. And if I come down here, I'd be noticing positive. There's no negative end. Okay, so polar has to have 2 ends. That's what we're talking about. Now, let's imagine that this diagram, this oval, is just representing the overall molecule. And it has a positive end and a negative end. So then it's polar. Well, the negative end of one molecule is attracted to the positive ends of the other molecules. So the positives want to get in here. The positive end of a molecule is attracted to the negative ends of other molecules. And so every positive really wants to be surrounded by negatives, and every negative wants to be surrounded by positives. So even though this molecule is a distinct unit of atoms, and this molecule is a distinct unit of atoms, there's little attractions between the molecules. And the more polar these molecules are, the stronger the attractions between the molecules. So the polarity of the molecules causes the molecules to stick together, to cling together. They're attracted. Positive of one is attracted to the negative of the next. All right, pop quiz. So now we're looking at which of these diagrams best represents how polar molecules will line up with each other. So, not entirely certain how the video quality is coming across to you, so let me just kind of read off. That says positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. This one says negative, positive, negative, positive, negative, positive, positive, negative, negative, positive, negative, positive, negative, positive. This one says positive, negative, 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 positive, negative. And this one, negative, positive, positive, negative, negative, positive, negative, positive, positive, negative, negative, positive, negative, positive, positive, negative, negative, positive. Which one is the best? Did you come up with A? If we look at A, like the positive end right here, when we look at it, all its neighbors, there's a negative end, there's a negative end, there's a negative end. If we look at the negative end here, it's surrounded by positive, positive, positive. All these others have at least one area where there's a problem. Like right here, positive, well, it's next to the positive ends, there and there. It doesn't like the positive ends. Positive, well, it's next to a positive end there and there. It doesn't like that. So the other ones all have some problems. This one has some really major problems. That would fly apart in a hurry. Okay, but A shows the best packing arrangement of charges. All right, so here's what we're going to do. Because water is polar, it leads to the properties of water. And strong surface tension, high melting and boiling points, high heat capacity, and the ability to dissolve many other substances are some of the properties we will talk about here. All right, let's talk about dissolving first. Okay, there's a lot of substances that are made up of charged particles. Okay, now water is polar. There are other substances that are called ionic, and they're literally made up of opposite charged ions, negative ions and positive ions. So if we picture that, if you can imagine a negative ion, the positive end of water would be attracted to the negative ions. Opposites attract. And for a positive ion, the negative end of waters would be attracted to it. So let's imagine you take a bit of table salt, sodium chloride, and drop it in water. Well, sodium chloride is made up of a network of these positive and negative ions. So here comes the water molecules, and the water molecules all start to grab hold. Like the positive ends of the water surround the negative ions. And, if enough water molecules get around one, they can pull it away. Here's a sodium ion that's been surrounded by the negative ends of waters and pull it away. And so over time, there's lots and lots of water molecules. They just keep pulling these ions apart. So if these ions get surrounded by enough water molecules with the right directions, then this gets pulled apart. So what's going to determine if something dissolves in water has to do with the overall attraction between the water molecules and the ions and these ions for each other. Not all substances dissolve. Sometimes the ionic attraction is stronger. But water dissolves more different substances than anything else that we know of. Right? Couple of properties that I'm going to throw in here. The words are cohesion and adhesion. Cohesion and adhesion. And I'll give you some definitions. Cohesion are when molecules of a substance are attracted to other particles of the same substance. So this is like water molecules are attracted to other water molecules, which is very true. Adhesion is when molecules of a substance are attracted to the molecules of other substances. So let me show you a little bit about cohesion and adhesion. I am hoping this can show up on the camera. So right here I have a fancy glass tube that's got all different sizes to it. I'm going to turn this around. Okay, I really hope this is focusing in for you. I won't know until I look at it later. I'm going to pour in, this is just water with some food coloring in it. Now, I don't know if you're going to be able to see this. Let me... Alright, we'll give that a try. So, can you see, I'm going to have to put this down, that of these 5 tubes, the water level is lowest in this one, and it gets a little bit higher, 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 and higher. And the skinny tube is so thin you can barely see the color of the water. The reason, I hope that you were able to see at least these couple in here. The reason it gets higher is because water is actually more attracted to the other molecules of the glass than it is to itself. And so literally it's climbing the tube. That's kind of funky to think about. That's an example of adhesion. Water is attracted to the tube. Let me try to show you a different one. Here's a glass plate. And I'm going to put a couple of drops of water on there. And I'm going to put another glass plate on top. And then, this is really hard to show you. I'm trying to grip. In fact, let me grab over on the edges here. Okay, I am gripping only the top glass plate. The bottom glass plate is very free. It moves very easily this way, but it sticks. And the reason is because the plate on the bottom is attracted to the water molecules, which in turn are attracted to the plate on top. Okay, the glass plates don't stick to each other very well, but both glass plates stick to the water, and so that makes it possible for me to suspend one glass plate from the other. One more example. And again, I think you're probably not going to be able to see this. Maybe. When you look at this tube here, there's water coming up to this line. And this is a glass tube. And the water literally curves upward all around the edges. And that's because the water molecules are more attracted to the glass than to themselves, and they actually climb the sides, and that leads to this curved surface in here, which is called a meniscus. You have a meniscus in your knee, which is a little curved piece. Alright, so adhesion is attracted to others. Cohesion is when they're attracted to themselves. So if I dip my finger in the water, there's a drip of water hanging from my finger. Why does... Well, you could say the water is attracted to my finger. That you might think is adhesion, but really, if you think about it, what's my finger made mostly of? My finger is made mostly of water, and so really, it's kind of an example of cohesion, the way water molecules cling to each other. So the prefix co means together. Okay, going on. Cohesion, we can imagine the water molecules all linked together. So imagine these little dashed lines are all attractions. And the molecules cling to each other. Here's my glass plate example. Adhesion, the molecules are all attracted to the plate as well as each other. When the molecules were climbing the tube, when we had a skinnier tube, the molecules climbed higher. And that's because of the attraction for the walls of the tube. Here, you know, it climbs towards the edge of the tube, but in the middle, gravity's pulling it down. All right, next one we're going to talk about is surface tension. because these molecules all cling to each other, they almost form kind of a network. Okay, each, this molecule is held tightly together, this molecules, but they link to each other. And if we put enough links, we can support things. Now, in class, what I would do is I'd get about 6 or 7 volunteers, and we'd form 2 lines, and we'd hold hands across the line. And then I'd get somebody else to stand on a chair and do a trust fall backwards onto our hands. And, usually we start out with somebody little and skinny doing the fall, and then we say, well, why not somebody a little bit bigger? Now, I've never quite trusted myself enough to try that, but we get some bigger person in class and let them fall back. And you know what? It's as easy as can be to hold them up with enough hands. I sometimes think you could think about it going to a rock concert and somebody's crowd surfing. They're going across the top of all those hands. And if there's enough hands, they don't fall through. Okay? So for this one, be patient with me just a little bit. I'm going to adjust my camera, I hope. Alright, so I have a container with some water in it and paper clip, and I'm going to put the paper clip on the water. What I like to do is make myself a little shelf bracket. I'm going to set a paper clip on top of that, and I'm going to lower it very slowly onto the surface of my water. And we have a paper clip which is made out of steel, and steel has a density somewhere more than 7 grams per cubic centimeter, and it's floating on water that has a density of 1 gram per cubic centimeter. And just from the standpoint of density, that makes no sense whatsoever. Now, I don't think I can get the camera in here well enough. Maybe you can see it a little bit in the camera, that the paper clip actually seems to push in the surface of the water. It's like the water has a skin on top, and the paper clip is sitting on that skin. And that's not a bad way of thinking about it. Actually, you can see that on the camera pretty decent now that I take a look. I'm impressed. That skin is because the water molecules are clinging to each other. So I'm going to go back. Hope I'm not making you seasick. Okay. Go back up here. Have you ever done a belly flop? There's Mr. Rupp. Good old Edgar Wildcat shorts there, green and yellow. Okay. And when you hit the water, that water seems amazingly hard. Well, that's because the water molecules are clinging to each other. They don't want to move out of the way. Surface tension. Okay. I'm going to go past this one. I already talked about meniscus. I'll mention density briefly here. Density is a measurement of mass per volume. Okay, so you take the mass of your substance divided by the volume it occupies. Water has a density of about 1, and it changes with temperature a little bit. What's really weird is that water, when it freezes, actually becomes less dense. And very, very few substances that we know of do that. Now, it only does it in a couple of degrees right near the freezing point, but that's important. I'm not going to go over pH scale with you. I have no idea what I was doing with that picture. That's important, but we'll come back to it later. All right. Here's a graph of boiling point versus some molecules. This molecule is H2S, H2SE, H2TE. Now, what's important to think about is if you were looking at a periodic table, S is right below oxygen, and Se is right below S, and Te is right below Se. This is sulfur, selenium, and tellurium. They're in the same column on the table with oxygen. So this is a graph of the oxygen family of elements all bonded with 2 hydrogen. So if we go over here, that would be H2O. Now if you look, it seems to be that there's a trend, right? So if we go from the bottom element towards the top, the boiling point's getting lower, lower, and so we're guessing for water that it'd be kind of low. Now here's the reality. When you go from H2Te to H2Se, the boiling point gets lower. H2S, boiling point gets lower. But when we go to H2O, this thing takes a sharp bend. What this tells us is that water has a much, much higher boiling point than what we expect from the size of the molecule. How can you explain such a high boiling point for that molecule? And it comes back to all these molecules are attracted to each other. And I want you to really think about this. In order for us to melt something, we have to break some of the attractions between the molecules. We have to let them apart. In order for us to boil something, we have to totally separate the molecules from each other. All right? So the more strongly they're attracted to each other, the higher the boiling point. You know, I want you to imagine my hands are molecules, and if this is my attraction, okay, this little pinky grip I have here, if this is the attraction between the molecules, it's pretty easy to break those molecules apart. If this is my attraction between the molecules, it becomes much tougher to break that attraction apart. The stronger the attraction between the molecules, the higher the boiling point. So water has a very strong attraction. So it's a small molecule. Most small molecules are gases at room temperature. Water doesn't boil until 100 degrees Celsius. That's an amazing thing. Okay, I think this is the last property we're going to get into, and it's called heat capacity. Hey, we're in the middle of May. My wife and I, we put up a little backyard pool in the summer, and we're already talking about it that, you know, maybe next weekend for Memorial Day weekend, we might put up our little pool. And, you know, when you fill it out of the well water is coming out of the ground at 50 some degrees, 50 to 55 degrees. That's not real comfortable for swimming. And you know that even though next weekend is looking to be around 80 degrees outside, the water's not going to be ready to swim because it takes a long time to heat up that much water. It's because water has a really high heat capacity. And how can we explain that? Well, again, think about all these attractions. Now, let's say I just want to warm the water up. Not boil it, just warm it up. To warm it up, I still effectively have to pull these molecules apart a little bit. I have to pull them apart enough that they have a little bit more room to move around. And because they're so strongly attracted to each other, that takes a lot of energy. A substance that doesn't have this attraction between the molecules is much easier to warm up. Okay? Because water has a very high heat capacity. And that's where we're going to stop. So I got some questions for you to answer. Hey, we're down to the last couple of weeks. Stay with it. I'll try to keep the assignments reasonable for you, but you got to expect to do something every day. And if you're behind, catch up. Call me. Work with me. I'll help you. All right? Take care.